This is Bio 181, Chapter 8. We're looking at photosynthesis, and we're looking at how light is absorbed. So we're going to start with the key concept. Electrons that are found in molecules that are called pigment molecules are the ones that absorb light energy. And light energy comes in packets called photons. So light energy is coming in from the sun, right? It's traveling. Oops. And actually, it's fine. I was going to pick yellow, but light energy coming in, what we see is like white light actually has multiple different wavelengths in it. So white light, if you put it through a prism, you'd actually break out into blue and red and green light, okay, among others. Let me move this like that. So green here. And oh, delete that. Trying to make it an intermediate frequency here. So not maybe that. Okay. Okay. So within white light, you have different colors of light coming in. And each of these different lights has different energy and a different wavelength. So red light happens to have a longer wavelength. So this is longer wavelength, okay? And wavelength, we typically use this symbol called lambda. I'm just going to write it out, wavelength. Okay, and this might be something like 700 nanometers. So that's pretty small. That's 700 times 10 to the negative 9 meters. So it's really little. But for light, for visible light, this is kind of on the longer end of the spectrum. So red light tends to be a little bit wider. And when I say wavelength, that's the distance from the start of one crest all the way down to the trough and then back up again. So this distance here, if I called that X, that's the wavelength. So you can see the wavelengths here. I'm going to go up this picture. So this wavelength, right, from across, let's just start here, back up to here. Oops. All right. So that wavelength is longer than, hopefully, if I did it to scale, this wavelength. And that one is going to be even longer than this wavelength. So the wavelength is longer for red. And then as you move towards blue light on the spectrum, then you're going to have a shorter wavelength. Shorter wavelength is going to have more energy. So more energy. Okay. And you probably are familiar with Roy G. Biv, right? So I'm just going to write it in black, not to be confusing. So red, orange, yellow, green, indigo, I forgot, blue, Biv, blue, indigo, and violet, right? So that's like a rainbow. And really what a rainbow is water acts as a prism in the sky, water droplets, and it refracts the light. It bends it to different angles based on the wavelengths, and that's why you see a rainbow. So it's basically acting like a prism and splitting them out. Now, anything that has a pigment molecule in it, so say in a leaf, you've got a molecule, okay, and that molecule is going to absorb light. So if it absorbs the light, it is called pigment. Okay, so pigment. Pigment is also in paint. They tend to be colored. They absorb some light and reflect others. So a pigment molecule, yes, like I said, it's going to absorb photons. Light energy in general, this spectrum is called electromagnetic radiation. Electromagnetic radiation. Okay. And it's going to, this range, it's all photons, and it's going to go from very high energy, like X-rays and gamma rays. So these have extremely high energy, very, very small wavelength. And then through visible light, which is in the middle, which is what we see. It's what there's the most of on the planet, which is why we have evolved to have eyes that see in this range. And then at the other end would be like radio waves. Okay. So there's a spectrum that falls onto the earth. Most of the light from the sun is emitted in the visible spectrum. Again, that's why plants use it. And plants are going to use blue light and red light primarily. So those are the two colors. So blue light and red light get absorbed, and then the green light actually just comes in and then bounces off, which is why leaves look green. It's because they're actually reflecting the green light while they're absorbing the red and the blue. So if we're looking at a diagram of what colors and what wavelengths are absorbed, there are two similar graphs. One is called an absorption spectrum and one is called an action spectrum, and they're very similar. So this is going to be wavelength, or you could put frequency down here. Those are both ways to represent different colors of light. H, right? And the units would be nanometers, right? So same thing over here. I'm just going to write wavelength, oops, and then nanometers. Okay. And then this is going to be for the absorption spectrum. So this is going to be, so maybe it would be like the percent absorbed, okay? And you're going to see that I'm going to just write down the colors down here. So if we start with blue, which is maybe about 400 nanometers, indigo violet, then we go to green, and then we have red. Okay, red's going to be about 700. So maybe this would be about, I don't know, 550 for green. Oh, gosh. It's barely in the blue, not so much in the green, and then primarily in the red. This is the absorption spectrum. This can be made for every different pigment molecule. So you could find an absorption spectrum chlorophyll. CH. PH. So that's the name of a pigment molecule. You'll have a different one for different pigments. So different, they're going to absorb slightly different wavelengths. And then you're going to have the action spectrum. And this is basically a set of the wavelength that's going to power photosynthesis. So this is power provides photosynthesis. So it's going to be a very similar one. So really it's going to have the same peak in the blue, and it's going to be different. The red has more energy in terms of the wavelength, so it might be a little bit less over here. Going to have similar. Panel, like a solar panel. So say you have this on your house and you want to save a little money, you want to have a solar panel. It's going to actually eject electrons. Those electrons are going to run through is how we get energy from solar panels. That mechanism is going to be called the leaf. You figured it out before we did, but so you've got a leaf. Here's my leaf. we have light coming in, it's being absorbed. And if we zoom in on the cellular level there, so on the single cellular level, into chloroplast, right? And then we're going to zoom into the chloroplast where the light is actually absorbed. And in that region, we're actually going to eject little electrons. Those electrons are going to run through the electron transport chain. The electron transport system is synthesis, but it's so. And we're going to use that to do work. And use that energy to do work the same way that you would use electricity to do work in your house. Okay? Except that in the solar system, it's going to take that energy and it's going to use it to make the hydrogen ion gradient. Okay? So it's going to use that to make the hydrogen ion gradient. Here, this is absorbed. It's called a photosystem. So it's solar panel, it's a photosystem. There's an antenna complex. That's where the light is absorbed. Right? The light is absorbed. And then that energy is going to be transferred into electrons. So the light energy is going to actually be converted. Remember, conservation of energy. Light energy is going to then be converted into potential energy in these electrons. And those electrons are then going to be moved to the reaction center. In the reaction center, those electrons are then going to be used to split. The water is going to be split. We're going to make gas, hydrogen ions, and we're going to